This example explores some of the challenges typically encountered in a hit-to-lead project. The objective in this case is to identify one or more high-quality chemistries for progression to detailed in vitro and in vivo studies based on initial screening data for potency. Ideally, the compounds chosen for progression should not only be potent, but also have appropriate ADME properties to result in high-quality lead series. We will also use StarDrop to explore potential modification of one of the existing compounds to improve its properties. We start by opening the file neurokinin2.sdproj by using the File Open menu. This project has a spreadsheet containing 191 structures and the measured affinities for neurokinin-2 in the column NK2-PKI. To explore the chemical diversity of this library and the distribution of potency across it, we're going to first take a look at a chemical space plot of this data. Click on the Visualization tab on the left. Click on the Chemical Space button and then the Create button to create a new chemical space plot. In the dialog box that appears, type in a name for the chemical space plot you're about to create. This example, we've called it neurokinin-2 space. It's possible to build different types of chemical space plots based on chemical structure and/or property data, but in this case we're going to use the defaults: chemical structure only, the visual clustering method, and 2D. Click the OK button and wait until the chemical space has been created and the dialog box disappears. When the process is complete, a chemical space will be displayed in the Visualization tab. Each point in the plot corresponds to one compound in the dataset. Hovering the mouse pointer over a point will show the compound structure. Selecting a row in the dataset will select the corresponding point in the chemical space and vice versa. To see the distribution of pKi values across the chemical space, we need to change the key. Click on the block of color next to neurokinin-2 in the key to bring up the Format by Property dialog. We change the source for the color to NK2-PKI and click OK. The compounds with the highest pKis will be highlighted yellow, the lowest red. You'll notice that a large proportion of the compounds with the highest pKi values come from one of the clusters in the chemical space. This may be the best region in which to focus for selecting compounds, but first we should consider the other properties that are important in a high-quality lead. We're going to keep this plot to use later, so click on the Detach button in the Visualization tab to create a separate window containing the plot. For now, we're going to minimize this window to keep it out of the way. We have no further measured data at this stage, so we're going to generate some predictions of ADME and physicochemical properties. Click on the Models tab. To run all the StarDrop models, click the checkbox next to the word StarDrop. This will select all the models under this branch. Click the Go button on the Models tab, and a progress bar will be displayed while the predictions are calculated. When this process is complete, you'll see that a new column has been added to the dataset for each property calculated. Scroll across the dataset to see the numerical and classification predictions that have been made. Due to the volume and complexity of the data, it's challenging to find the compounds which have the best balance of properties, so we're going to use StarDrop's scoring tool, which will make it easy to assess all of this information together. Click on the Scoring tab. A scoring profile enables you to define a set of criteria that is important for your project. StarDrop has some example profiles built in, and as part of the project file, we have already loaded a profile designed for this neurokinin-2 project. A scoring profile contains a series of properties along with criteria describing desired values and their relative importances. In this profile, we're looking for compounds with good affinity for neurokinin-2 and which are suitable for a peripheral target. Run the scoring profile by clicking the Go button on the Scoring tab. A new column will be added to the dataset containing a score for each compound, taking into account the property criteria and their relative importance in the profile, as well as the uncertainty in the underlying experimental and predicted data. The score is a value between 0 and 1, representing the likelihood of success of the compound against the profile we have defined. To find the highest scoring compounds, right-click on the scoring column header and choose Sort Descending to sort the dataset from high to low score. The histogram in each cell gives a quick overview of the impact of each property on the score for a compound. As you scroll down the dataset and the scores become lower, the low bars in the histograms indicate properties that have not met the requirements defined in the project profile, taking into account the confidence in the data and importance of each property. Having scored the compounds, we're now going to compare some compounds using StarDrop's card view. This provides a convenient way to work with our compounds and data in the context of this project by representing compounds in cards that can be moved, stacked, and linked however we wish. Switch to Card View by clicking the Card View icon on the toolbar to the right. This will display a grid of cards. You can choose which properties you would like to see on a card, but in this case we have already created a card design that shows the scoring profile and some of the properties in which we are interested. Sort the grid in order of the score from top left to bottom right by choosing the grid option from the layout menu at the top of the screen. We can now colour the cards to highlight the most potent by clicking on the Colour button, and in the Colour by dialog choose to colour the points by NK2 pKi. We can easily compare two compounds by placing the corresponding cards side by side. Click on the highest scoring compound and drag it to the top. Now select the fifth compound, which is one of the most potent, and drag it to lie beside the first. You can now zoom into these cards to look at them in more detail by pointing at the cards and using the mouse wheel, or if you don't have a mouse, by holding down the Control key and pressing the equals key. Dragging the background will also help you to position the cards conveniently. Here we can see that the compound on the left has a higher score, even though the compound on the right is one of the most potent. We can investigate this further. Click on the second circle on the bottom of a card to change to the second page. Here we can clearly see that the compound on the right has high log P and Hg PIC50, which increase the risk for this compound and hence result in a lower score. Having compared individual compounds, we would also like to explore how the properties vary across the different chemical series in this library. Clustering provides a convenient way to group compounds by chemical similarity. From the Analyze menu at the top of Card View, select Clustering. In the Cluster dialog box, choose the Common Substructure method, set the similarity to 0.65 and click Cluster. The compounds will be grouped by common substructure to form stacks containing multiple compounds. The stacks will be positioned such that stacks with similar common substructures will be close. Zoom in on the stacks corresponding to clusters 4, 7 and 10, which will be close together, and drag the background to center these in the display. You can move the stacks to separate them slightly by clicking and dragging. Here you can see that although the compounds are in different stacks, this is an artifact of the cutoff assigned to the clusters, and these groups all share the same quinoline scaffold and could be considered a single series. We can easily combine these by dragging one stack on top of another. We can then assign a name to this series by clicking and editing the label under the stack. We could examine the other stacks and repeat this process where necessary to refine the clustering results. However, to save time, we have saved the series definition in the dataset and can use this to stack all of the compounds. From the Organize menu at the top of Card View, select the Stack by Property menu option. In the Stack by Properties dialog, choose Series from the Stack by drop-down menu and click OK. We can see that there are 6 series, of which the amide oxime series has the highest average potency. It's the most yellow. We can display more information on a stack. To illustrate this, we can choose a new stack design. Select the Custom menu option from the Design menu at the top of Card View. In the Card View Design Preferences dialog, you can change card sizes, choose which properties should be displayed, and how the properties should be arranged. But in this case, we're going to choose a predefined template saved as part of this project. Select NK2 Card Template and click OK. The resulting stacks show a histogram of the distribution of pKi values of the compounds within each stack, and below this, a box plot showing the distribution of scores. This makes it straightforward to compare different series. For example, the amide oxime series has an excellent distribution of potency. However, the large majority of scores are very low due to poor results for other properties. In contrast, the phenylpiperazine series has fewer potent compounds, but a significant proportion of high-scoring compounds, suggesting that this would be a good series to investigate further. We can explore the distribution of scores across the dataset as a whole by returning to the chemical space plot we created earlier. In the chemical space plot window, click on the block of colour next to neurokinin 2 in the key in this window to bring up the Format by Property dialog again, and, as we did before, change the source property to be the NK2 project score values. This way, the points will be coloured based upon the overall scores of the compounds, not just the pKi values. Here we can see that the pattern has changed dramatically from that which we could see when looking only at potency. There is just one small cluster of yellow points as a hotspot of high-scoring compounds. Select the phenylpiperazine stack to see that this corresponds to the hotspot in chemical space. Although this appears to be the best series, we should consider the impact of the uncertainty in the underlying data on our ability to confidently distinguish between compounds. Therefore, we will use another type of plot to explore this. Click on the Visualization tab again. Now click on the Snake Plot button on the Visualization tab to change the plot type. A snake plot shows the scores on the y-axis for all compounds in order from highest score to lowest score along the x-axis. The overall uncertainty in each score, due to the uncertainty in the underlying data, is also applied as an error bar around each point. Looking at the snake plot, we can see that the top 30 compounds cannot be confidently distinguished from the top scoring compound. Notice that the error bar for the top scoring compound overlaps with the error bars of approximately the top 30 compounds. Therefore, we should consider selecting compounds from this range to further explore their properties and make a confident selection of potential lead series. Selecting the top 30 compounds in the snake plot by drawing a ring around them with the mouse highlights where these lie within the chemical space and within the stacks in card view. Notice that this selection includes compounds from different regions of the chemical space and a small number of compounds from every stack except the monobasic ether oxime series. This suggests that some of these chemistries cannot be rejected with confidence. Therefore, it may be more appropriate to sample a small number of compounds from some of these alternative chemistries to generate some experimental ADME data. These data will have lower uncertainty than predicted values, and hence we will be able to identify with greater confidence the chemistries that will yield a high-quality lead series. Having looked at the data across this library, let's focus on the phenylpiperazine series to see if we can identify any interesting structure-activity relationships with which to guide the design of further improvements within this series. To do this, select the phenylpiperazine series stack and then click the Create from Selection button in the toolbar on the right. In the Create Dataset from Selection dialog box, give the new dataset a name, e.g. phenylpiperazine series, and click OK. This will create a new dataset containing only the 15 compounds from this series. We can sort the cards in order of descending score using the Sort By dialog by clicking on the Sort button in the toolbar on the right. The score column NK2 Project is the first one in the dataset and will already be chosen, so click OK. We'd like to look at these compounds in more detail, so we'll load a new card template that displays more data on each page. When loading a saved card template that is already part of a project, it's not necessary to open the Card View Design Preferences dialog because the template will be available in the User Designs menu. Select the Design menu, then User Designs, and then Phenylpiperazine Card Template. We will use the Activity Neighborhood analysis to explore how small structural modifications can influence potency around the highest scoring compounds. This is also known as activity cliff detection. Select the card in the top left of the grid. This is the highest scoring compound in this series. Then select the Activity Neighborhood menu option from the Analyze menu at the top of Card View. The Activity Neighborhood tool compares each compound with the selected reference compound and arranges these in order of structural similarity. The nearest neighbors are linked to the reference, and that link can be colored by the change in the selected property. In the Activity Neighborhood dialog box, link the default number of nearest neighbors, 10, and choose to color the links by the difference in NK2 pKi. Then click OK. The resulting display shows the reference compound in the center and the remaining compounds arranged in a spiral in order of decreasing similarity, increasing distance, from the reference. The 10 closest compounds are joined to the reference by a link. The arrow indicates the direction of increase of the selected property, in this case NK2 pKi. The color indicates the magnitude of the change, in this case from red being the largest to grey being the smallest. Therefore, a short link with a strong red color indicates an activity cliff, i.e. a small change in structure that gives rise to a large change in activity. One example of this can be seen between the reference compound and its closest neighbor. Zoom into the central compound to compare it with its closest neighbor, using the middle mouse wheel or Ctrl and equals keys. Here we can see that the replacement of the pyrrole group with a phenyl has resulted in a 1.5 log unit improvement in potency, from 25 nanomolar to less than 1 nanomolar. However, the overall score is reduced because of an increase in log P and Hg PIC50, as we saw earlier. We might wish to explore alternative approaches to improving these properties while retaining potency against the target. To do this, we can use Molecule View and the Interactive Design tool with Glowing Molecule. Select the compound on the right and click the Molecule View button on the right-hand toolbar to switch into Molecule View. This shows an overview of all the properties of the compound at the top. You can scroll through the compounds using the left and right arrow buttons, and clicking on the score cell will show a heat map indicating the contribution of each property to the overall score. Switch to the Design tab, and the selected compound will appear in the Interactive Designer. click on the Hg PIC50 value in the summary table in molecule view. This highlights each molecule using StarDrop's glowing molecule to indicate which regions are having the greatest influence on the predicted value for Hg PIC50. Areas highlighted red tend to increase the predicted property value, and areas highlighted blue tend to decrease the predicted property value. Therefore, to reduce Hg inhibition, we should remove a red region or add a blue group, bearing in mind that the substitutions might be beneficial or detrimental to NK2 potency. Note that the basic piperidine nitrogen and adjacent linker is highlighted in red. We will change this amine to an amide and explore the impact of this change. Select the bond tool and click on the carbon chain atom next to the amine. While the mouse is clicked, drag away and then release to draw a methyl group. Now click on the new bond you have drawn to make this into a double bond. Finally, point the mouse at the carbon at the end of the double bond and press the O key to replace the carbon with oxygen and complete the amide. Notice that the amide oxygen has a blue glow, indicating that it is having an effect to decrease the predicted Hg PIC50, and that these changes have not only reduced the predicted Hg affinity, but have also reduced the log P. To add this or any other compound you design into your dataset, simply click the Go button in the Design tab. At the top of the summary table, you'll see a question mark against the score. This is because we do not yet have an experimental pKi value for the NK2 affinity for this new compound. To generate predictions of NK2 affinity, we can use StarDrop's automodeler to build a new model of the data we have. You can find a worked example of StarDrop's automodeler, along with walkthroughs covering all of StarDrop's features and modules in the tutorial section of the Optibrium community.